13,600K, which operates at the clock speed of 5.1 gigahertz. And in modern CPUs, you require one CPU clock cycle in order to access a CPU register. So one CPU register access, one clock cycle. And the question now is, how much time is needed for one register access? And the question is, how much time in a sense of a time unit? So how many seconds or milliseconds or microseconds or nanoseconds or picoseconds it requires, actual time unit, in order to access one register. Before that, gigahertz means there's the same factor as we saw before in data sizes. Like below gigahertz, there is megahertz, and then there is kilohertz, and then there is hertz. 1 hertz means 1 operation per second. So this is 1 hertz, 1 operation per second, or 1 instruction per second. A kilohertz would be then times 1000. So the factor in order to transform like hertz to kilohertz would be 1000. Decimal prefixes 10 to the power of 3, 1000. So 1 hertz or 1 kilohertz is 1000 hertz. 1 megahertz is 1000 kilohertz, and 1 gigahertz is 1000 megahertz. So 1 gigahertz is a lot of hertz, and 1 hertz is 1 instruction per second. And the question now is, how much time for one register access? I will give you time to work for this. Let's do 10 minutes. So you have 10 minutes time to figure out how much time is needed for one register access. And if you think you have a solution, just put it in the chat such that I can see, well, how many people can actually achieve it and how many have the correct answer. And after 10 minutes, I will present you the solution. So yeah, let's do it. We talk in 10 minutes.
Can you please show the slide again?
Test. I would rather have the countdown shown here. Please download the slides and work with the slides offline. Okay, let's see. 10 minutes are over, and I saw some correct answers, but unfortunately, the majority is wrong. And this is like the question, like the approach is quite easy, right? So we know 1 hertz is 1 instruction per second, and we know like the formula from school that if you want to have the time, it's 1 over the frequency that we have, right? And the frequency is 5.1 gigahertz. So what we have, or what we need to calculate if we want to have the time, is the frequency in gigahertz. So we have 5.1 gigahertz. And 1 gigahertz is 10 to the power of 3 megahertz. 1 megahertz is 10 to the power of 3 kilohertz, and 1 kilohertz is 10 to the power of 3 hertz. Hertz is 1 instruction per second. So what we must not forget is the unit, which is seconds. So basically, the answer is in 1 over 5.1 times 10 to the power of 9 seconds. This is a very small number, but this is it. How small is it? Well, we know 1 gigahertz is 1000 megahertz, which is 10 to the 1000 is 10 to the power of 3, right? So 1 megahertz is 1000 kilohertz, and 1 kilohertz is 1000 hertz, right? For time, 1 second, oh, let me correct that. So 1 second is 1000 milliseconds. 1 millisecond is 1000 microseconds. 1 microsecond, oh, wrong. 1 microsecond is 1000 nanoseconds. And 1 nanosecond is 1000 picoseconds, right? And we do not get below the picoseconds. If we take a look at this, well, then we can get rid of the seconds, in where we say, well, we don't want to have the answer in seconds. We want the answer in milliseconds, for example. And as the factor between a second and a millisecond is 1000, I need to multiply this number by 1000, which is 10 to the power of 3. Then, well, milliseconds, this is just a small number as well. If we want to have microseconds, we add a factor 1000. We want to have nanoseconds. Yeah. We add a factor 1000. And you see where we get here with our calculation. We can cancel now, because we have in the numerator and the denominator a lot of factors 10 to the power of 3. So we cancel this, we cancel that, we cancel that. So what we have now is, oh well, I will move it below. So we have, wrong color, 1 over 5.1 nanoseconds. This is the answer. And if we put that into the calculator, calculator, switching to the desktop. I don't know if you see it. It's rather small, but if I calculate, well, 1 over 5.1, then I get an answer of, write that down, 0.19607 and so on. Switching over to my tablet again. So this is the answer. By the way, if you're confused why I write this comma here, so this is muscle memory. In Germany, you separate the digits after 0 by a comma. In an international context, you would have a dot there. But I mean, I'm German, so my muscle memory is to have the digits after the decimal point separated by a comma. You should think about the dot here. I will correct this mistake. So we will have a dot here. So it's 0.196 and so on nanoseconds. This is still a small number. We can add 1,000 to here as well. So times times 10 to the power of 3 gives us 196 picoseconds, which is the correct answer. So let's mark this. This is the correct answer. So for those who have 196 picoseconds, this is absolutely correct. And the task is not as trivial as it first looks like. The task trains you to work in the right units. And this is important for this kind of calculations. And it gets more important when we talk about bandwidth and data rates in the network parts. Oftentimes the calculations, the numbers are easy, but you need to take extra care about the units. Switching between units is important because this is one major part of your solution. So don't forget units. So if you do not calculate in units, then this would be a rather bigger malus in your solution, and focus in transforming between units. So you need to know that 1 second is 1,000 milliseconds. 1 millisecond is 1,000 microseconds, up until picoseconds. So picoseconds is the smallest that we have. And I guess in terms of kilomega giga, the highest that we calculate, I guess, is tera. So you don't need that. You don't need the knowledge that 1,000 terabyte are 1 petabyte and 1,000 petabytes are 1 exabyte. So we stop at tera and at pico. Okay. Congratulations to those who have the right answer. Perfect. So next. I mean, we talked a lot about things today, but the module is called Operating Systems and Networks, and all this computer architecture and the calculations on units. Well, what is the point that I want to make regarding operating systems? And all these hours/minutes, I want to emphasize one thing, and this is complexity, right? So computers are very, 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 very hard, complex systems and very hard to program. And for us as humans, it's impossible to understand every detail of every hardware component that is built into a computer, right? So it's not just programming the CPU. I mean, programming the CPU on a hardware level looks like this. It's also programming hardware, such as a hard disk controller, or how to get like values out of input devices, such as a keyboard or a mouse. This is very complex and nearly impossible for humans to understand because the computer's getting complex. In the 80s, for example, where we had basic consoles, like maybe someone remembers the Nintendo Entertainment System or the C64, so the Commodore 64 computers. These were still complex, but easier in a sense that they do not have as complex hardware components as we have right now. So in the 80s, very, very smart humans could understand the hardware and could program like on an instruction level. Right now, only the smartest can, and it's very, very cumbersome. So what we need is something. Oh, where's my mouse pointer? Oh, my presenter crashed. But you see the slide here. So in the meantime, when I restart this, you see it in the diagram here. What we need is to hide the complexity that the hardware has, because this hardware is very complex, by an interface that we as humans, as programmers, can use in order to work with computers and the hardware. And this is exactly the job of the operating system. Having the ugly interface of the hardware abstracted by the operating system, and the operating system provides a beautiful interface to us programmers that we can use. Question to the round: did you have your first Programming 1 lecture already? Yes. So I guess you did a Hello World, and you know what a system out print line is, right? So this line, system out print line Hello World, I assume that you're programming in Java. So this Java line, what this does internally is it communicates with the operating system, because the operating system is the hardware overlord. And the operating system then displays what you do in the system out print line and displays this to the monitor. So there is a lot of hardware in between, but from the software perspective, the system interface that you know from programming talks with the operating system and carries out the action that you want to do. And this is easy, right? So let me restart my slides, then I can show you some examples. Why is this so unstable? So please do not crash. Please do not crash. So restart the slide deck. It's so chunky on my end. So slide deck, next slide. Okay. I have to do it. I have to scroll through the slide deck a little bit slower, such that come on. Yes. Did not crash. It crashed again. I'm sorry. I need to do it again. And afterwards, I need to figure out why it is crashing. So with the whole stream and all the programs that are running, I guess I'm running out of CPU resources. Okay. And it's all started in the mid 40s. Computers were room filling. You see it on the picture here on the right-hand side. So this is the Colossus computer. The Colossus computer is famous because it was built in Bletchley Park. Does anyone know in the audience why Bletchley Park is famous? Does anyone know? No worries, I will tell you. There is one famous computer scientist that worked at Bletchley Park, and this is Alan Turing. Alan Turing is famous for a couple of achievements. The achievement that he's most famous for is deciphering the Enigma. So the Enigma is was an encryption device used by the Germans, and Alan Turing at Bletchley Park in England was the first that cracked the Enigma cipher, meaning that the Allies were able to decipher like messages sent by the German military, which was decisive for the outcome of the war. Last week we had Nobel Prizes, so Nobel Prize for chemistry and physics and such. There is no Nobel Prize for computer science. The equivalent for computer science Nobel Prize, so a prize in this kind of range, it's called the Turing Award, named after Alan Turing. So this guy Turing, also like father of AI, father of a lot of theoretical computer science concepts and terms. This guy worked at the Colossus computer, like in the mid 40s. And the hardware that they used, they had no chips at the time. So the hardware that they used to perform basic arithmetic calculations are vacuum tubes, and out of these vacuum tubes, they built electrical relays. And there was no way of programming as we know it right now. So we have a display and we enter some code in there and then it runs. No, they had to put wires together in kind of a plug board. And the way how these wires were put into the plug board, this programmed the computer. So the input was a plug board, output was a printer. So you see it here, they had a printer and it printed out things. And obviously there was no operating system there. So directly like hardwiring electrical circuits on this kind of computer. The next generation, 10 years later, mid-50s to mid-60s, introduced a new generation of hardware. So there we had, for the first time, transistors. And computers nowadays, all chips are based on transistors. And maybe you know this like performance indicators that you read in the marketing of CPUs, the 5 nanometer process or the 3 nanometer process. This means the distance in the chip between two transistors. So if you are on a 3 nanometer CPU, means that all the billions and trillions of transistors in this chip are separated by a 3 millimeter space. So these transistors are packed super, super dense into this chip, and having more transistors in a smaller like package has some benefits, like it's more power efficient, you can achieve more performance and such. So transistors were introduced in the mid-50s to mid-60s. And there, for the first time, you can program these machines. So you see the machine on the right-hand side. These are the shiny days for IBM. This is an IBM 1401 mainframe. You see it's a relatively large box, and you put these boxes into computer rooms. In this picture, if you take a very close look, you see a second one in the background here as well. And if you take a super close look, there's a third one here in the background as well. So you had multiple IBM mainframe machines with a lot of wires and transistors and such, and these machines did some basic calculations in a computer room. This computer room was mainly in the basement because it's cool there, and you can put in some cooling systems, air conditioning systems in there. This was not the time of home computing. So only large organizations could afford computer rooms with this kind of machines, and most organizations were universities. So the main use case for computers in this generation were scientists that had a lot to calculate, and or research facilities as well, such as CERN. Absolutely right. And you have like people coming into the room and program these machines. Programming these machines was done via punch cards. Output was a printer. And you do not have an operating system. So what happens if you want to have your program running there is you would need to create these kind of punch cards. So this is a Fortran statement. So one line of code, and you see the code here at the top. This is a Fortran statement. I do not know Fortran, so I don't know what this means. But this statement, Z1 equals Y plus W1, this is like this kind of punch cards where you put in holes, and this represents then a statement. And this was groundbreaking because you program, or you create a program based on a high-level language as opposed to a low-level language. So remember all these instructions that we saw before. This is low-level language. This is machine language. These are the instructions that the computer can understand in the native machine language. If you program this way, we say you program in assembler. So assembler is basic computer instructions. If you program in a high-level language, as we do with Python, as we do with JavaScript, as we do with Java, as we do with all modern languages, we use a high-level language. High-level language meaning that you do not use instructions to put values in registers. You use operators and you use variables. And this is revolutionary. Like having a statement where you can have a plus operator, or like some other operators such as division operator or the power operator or the modulo operator, for example. This is symbolic computing. We have variables. These variables have values, and we can use symbolic operators to perform operations on these values. And this makes up high-level programming as we know it right now. This was for the first time possible with Fortran. Fortran today is still relevant. A lot of high-performance computing is done in Fortran, and it was basically the first programming language in existence. But this Fortran language, I mean, it's easier, way easier, by a couple of orders of magnitude. It's way easier to program in a high-level language than in a low-level language, because you do not need to understand the hardware when you when you program high-level. You need to understand the hardware. You need to know the instructions and what they do if you program low-level language, right? So people prefer to program on a higher level, meaning that higher-level programs need to be translated first to the low-level language in order to execute, because we know computers execute instructions. So we need to translate a program that is written in Fortran into assembler, because only assembler programs can run directly on the computer. It's the same time as we know it today. So if you program in Java, this Java code needs to be translated to assembler first before it can execute on a CPU. And this translation process is called compiling. And there is a program that's doing exactly that. And this program is called the compiler. So high-level language needs to translate it to a low-level language before. And as there is no operating system, the operations of a computer is done by a human. And what you see here is the method of batch processing. So in this generation, the second generation, we had no operating system, and the operating system was, or operating the machine was done by a human. This is the operator, like a human in between. And users, like imagine a large university with a lot of floors, and users in their offices put together programs and put holes in punch cards. So these users put the tens of thousands of punch cards into a box, and they run with the box to the basement and put or hand over the box with their Fortran program to the operator. And as the operator is smart, the operator does what we call batch processing. So the operator takes a look at what program this is, and the operator configures the machine according to the programs that were submitted to the operator. And the operator pools similar programs before, because different programs require different configuration of the machine, right? So these are still very complex machines with a lot of buttons and blows and whistles. And they, for specific programs, they need specific configurations. For example, a Fortran program to run on the machine requires the Fortran assembler, Fortran compiler, the Fortran compiler to be present in order to perform the translation. So this would be one of the configuration parameters. Is a Fortran compiler loaded, yes or no? And based on this kind of requirements, the operator pools programs with similar requirements, because the operator is smart. If we have 5 programs with the same requirements, you need to configure the machine once, then in sequence run these 5 programs, and then do the next batch. So the pooling of similar programs would be a batch, and you execute one batch with similar configuration after the other in order to minimize the time the operator needs in order to reconfigure the machine. This is called batch processing. And the goal is to reduce setup time for programs with similar requirements. Next generation, third generation, is the next step of progress. Now we have ICs, integrated circuits. So an IC is a chip, and we have transistors in chips now. In the mid-60s to the 80s, you can program these machines with assembler and Fortran as well. You can input in punch cards and tape drives. So you could have like magnetic cassettes. I don't know, I guess you're young enough. So tape, cassette, let me Google that. So these are the things where programs, you need to buy it on eBay now. These are the programs that you, these are the devices where you can put programs in it. So these are magnetic like bands, and you can store information there. And it's, I mean, you see it on the size. It's way more efficient than to have a program on a tape rather than on thousands, tens, and hundreds of thousands of punch cards. Output is still a printer. There is still no display, but for the first time, we have an operating system. So all the tasks that the operator needed to do before, like loading a program on the computer and running a program on a computer and reconfiguring the machine, this is done by software now. The first operating system that we know runs on these IBM 360 mainframe machines is OS 360. It's the operating system for this with 360 machine. And there are concepts that improved the efficiency and the look of feel working with computers dramatically. The first one is spooling. Spooling means that, or it comes from simultaneously peripheral operations online. It's a very heavy term for something, for a mechanism that is quite easy. It means that users, like they are in their offices and they program, right? And they have the program on a tape or on a punch card. And the mechanism is to load the tape to a hard disk. So computers have hard disks now, so persistent storage. And they load their programs from a tape to a hard disk as soon as they were brought to the computer room. And whenever a currently running program finishes, the operating system and not the operator loads the next program to execute from the hard disk and executes that. So before, you need to hand over your program to the operator, and at the time when the program executes, the operator needs to operate the machine by hand. In spooling, we have it asynchronous, right? So you bring your tape to the computer room, you load it to the hard disk, and then you can leave, because there is a software, the operating system, that is able to load a program from hard disk. And it's trivial for us right now because we do it all the time. But in this generation of computing, this is a new concept. Loading programs from a hard drive into memory. This works with inputs and outputs, right? So you can load a program, but you can load a program from hard disk, but you also can store results from main memory to the hard disk as well. And this made the life of users much easier because it reduces the waiting time for the users being in the computer room and a program still running for 2 or 3 hours. So they needed to wait at the computer room in order to slot, like a slot machine, they put their punch cards in the computer. So spooling, interesting concept, operating systems. The next one is multi-programming. It allows the concurrent execution of multiple programs. So, I mean, I talked about multitasking before. So one part of multitasking is multi-programming. And the idea is, well, we have main memory, right? And we execute the instructions from main memory. So what if we just have multiple programs in main memory? So in this case, in this example, we have 3 programs and an operating system in main memory. I mean, the operating system is still a program, right? It's the same concepts apply for operating systems as well. It's a program. But this operating system is able to control the execution of other programs. So the idea is to have multiple programs in memory and switch between these programs. One switch is performed if one program is waiting for I/O and does not use the CPU. And this happens all the time. So for example, my super flaky PDF presentation waits for me to input or to wait for me as an input from my keyboard in order to switch to the next slide or to the next bullet. And in the meantime, the program does nothing. So it just simply waits. And this, like waiting for inputs, like key presses, or outputs, like printing something out or displaying something on display, this is called I/O waiting times. And on average, every program spends 80 to 90% of total operation time using or waiting for input and output. So there is a whole lot of potential to reutilize the CPU in these waiting times. And this is exactly what multiprogramming does. So if one program is waiting for a keyboard input, or if any input, another program can take over and utilize the CPU. And this is called a context switch. So if program 1 is waiting for keyboard input, in the meantime, the CPU switches to program 2. If 2 is in the same situation, so it waits for some input, it switches to program 3. And this is the idea of multiprogramming. So doing context switches. Context switch involves saving the current program state and loading the saved state of the next program. So, I mean, this is the idea. And a context switch, be aware, this context switch is not as easy as it sounds, because you have something like register values, right? So we execute one instructions after the other, and depending on which instruction is currently executed, we have different values in the register. So imagine the compare instruction that we discussed before, when we compare 2 numbers. The result of this comparison needs to be stored somewhere, stored in a register, right? And if you switch from one program to another, then these register values need to fit to the program that is currently executed. So if you switch programs, you need to switch register values as well. And what the computer does is, when a context switch is performed, it saves like all the register values that are currently in the registers, puts them to main memory, and loads the register state from main memory from the next program and puts the values into the registers. And this takes a little bit of time. So these context switches are not for free. It requires a little bit of time to store and save the values, but still, it's still more efficient to do this context switch. Is way more efficient, like largely more efficient than just wait or being stuck in I/O waiting time. So multiprogramming, introduced in the 3rd generation, diminishes I/O waiting times and optimizes the CPU operational efficiency. The next concept is time sharing, and it's a logical extension of multiprogramming. So with multiprogramming, we allow multiple programs to be in main memory at once. In time sharing, we enable multiple users. So multiple users using the same machine, multiple programs being in the memory for the same time. So the idea of time sharing being that it enables multiple users to access the computer via online terminals. So again, imagine we have a basement, there's the computer room, a lot of computers are in there, and people are using the computers or are programming in their offices. And with time sharing, they had online terminals like input-output devices, displays, and keyboards in their offices, and they could communicate with the computer via these online terminals. And let me put up this slide. And the concept works as follows. Imagine that we have 8 users that want to use the computer and want to use the CPU. Then time sharing means that in a cyclic manner, every user is assigned a time slice where the user can use the CPU. So for example, the user has the CPU for 10 minutes, and then it goes to the next user. This user 3, he's on holiday, so it's an inactive link because it's a dashed line here. Dashed line means inactive link. So once the time slice of user 2 is over, next would be user 4 that's allowed to use the CPU for 10 minutes. 5 is inactive, then it would be user 6, then it would be user 7, then it would be user 1, and so on. In a cyclic manner, every user has a time slice where a context switch happens, and this allows multiple users to use the resources of the computer in a more shorter time. Because otherwise, well, user 1 would compute or would execute the program until it terminates, and then the next user is in line. Meaning that if some user has a large program that executes for 10 hours, in this 10 hours, no one else could use the computer. And if this program executes 10 hours and there is a bug in the program, so an error in the program that occurs like after 8 hours, then you have 8 hours wasted. So the error detection process is way enhanced using time sharing because, I mean, you have these time slices and you enhance the responsiveness of smaller programs. So you don't need to have like these large programs, you can have smaller programs, and you streamline the error detection process, which is a large improvement. Exactly. So this concept is time sharing, and this time sharing, or like the concepts of spooling, multi-programming, and time sharing are 3 examples of benefits that a software-based operator, an operating system as we know it today, brings a large benefit. And if we combine time sharing and multi-programming, we end up what we call multitasking right now. So multitasking meaning that you can run multiple programs at the same time, and that multiple users can use the same computer also at the same time. Note that this applies for servers and workstations as well. So it's possible in all operating systems that multiple users can log into a computer and perform some program or run some programs there. All right, so in the 3rd generation, you see it, 3 new concepts that were introduced with the operating system, or with 360. What we have now, from the 80s to right now, personal computers, it's the 4th generation. We have large-scale integration, so we have CPUs, we have chips, we have all the hardware components that we know. We program these computers with different programming languages, so modern programming languages are Python, Java, C and C++ as well. BASIC is a programming language that was pretty popular in the 80s, but no one programs in BASIC today. We have different inputs and outputs. We have floppy drives, we have CD-ROMs, we have USBs, we have a lot of inputs. We can input things from a network, and we can output on a display on a printer as well. We have a variety of operating systems. The major ones are Windows and macOS. So Windows with the biggest market share, Mac users, so Mac hardware users will have Mac OS as their main operating system. Some fringe people use Linux. I count myself to these people. And Linux is largely popular among computer scientists and developers. So Linux will be a target operating system if you want to pursue a career as artificial intelligence expert, because somewhere needs, or on some machine, these AI models need to be trained. So on some server. And you know, ChatGPT, I guess, burning 700,000 euros of computation costs per week or per month. I don't remember, but it's a large number. So these are server costs that you need to train this kind of large models, and all servers, without some very exceptions, use Linux as an operating system. So if you want to really, on an industrial grade, doing machine learning, you need to know your way around Linux, because this is the operating system that most servers run on. There's a fifth generation as well. I mean, literature distinguishes between the fourth and the fifth generation. Fourth generation being personal computers, meaning that computers were affordable, that you can have it at home. Mobile computers, well, everyone has a smartphone, and mobile computers are like small computers, right? So we have system on chips there. So all the components that we talked about before, like storage, M.2 SSD, and RAM, and the CPU, and all these components are put together on a single chip, and we call the system on chip. And we use it mostly in mobile, mostly because in the recent developments on Apple silicon, so Apple again doing pioneer work there, Apple equips MacBooks also with system on chips where RAM is integrated into the CPU package as well. But this is just for completeness. I mean, everyone knows how to run and operate a smartphone, what's the input and output, and what operating systems we have, such as Android or iOS. Rao, you have a question. Please go ahead.
Yes, sir. I have a question regarding the Ubuntu and Linux. Which one we will use, Linux or Ubuntu in this course?
We
And
use
which one is recommended?
So Ubuntu is a Linux distribution. So Ubuntu is Linux, and we will use that for the course.
I see. Thank you.
Okay, what we do next is let's do a quiz on operating systems. So throughout the history, I mean, the important thing of the history is not like the dates, well, when was this and that, but what is important for you is what concepts evolved, and how can an operating system bring value in operating this kind of complex machines. So this is because there was a question before, is this relevant for the exam? The answer will be yes. So now please switch over to iLearn. There's a quiz, history of operating systems, and let's do this quiz. So you do the quiz. Try to not just guess. If you do not know an answer, please look up the slides and aim for like a perfect score in the quiz. There are 8 questions, and let's do this quiz in 10 minutes. So let's see how many full points we have in 10 minutes. Let's go. Unmute myself. Okay, welcome back. There's a question in chat regarding the quiz. How can spooling be used for output? Well, if you consider spooling, I mean, the main approach is you have a tape with a program on, and you don't want to wait for the computer to have free resources in order to run the program. Therefore, you do spooling, meaning you load the program from your tape drive to a hard disk, and whenever the computer is ready to take up the next program, the operating system loads the program from the hard disk, and you don't need to wait in the computer room in order for your program to run. So this is spooling for inputs. For outputs, it's the same concept, but vice versa. So your program produces some results, right? And these results needs to be fetched by the user that is interested in this result. So with spooling, you have a hard disk built into the computer, and the operating system puts the results onto the hard disk. And if you want to fetch the result, you go to the computer room and you load the results to the tape drive. And the important thing is that you can do this not at the same time as the results are produced. You can do this asynchronously. So the software stores the results on the disk, and whenever you have time, you go to the computer room, load the results onto your tape drive, and be happy. So it's the decoupling of inputs and outputs need to happen at the time when the computer is ready. Like having an asynchronous way to provide the computer with inputs and getting the outputs from the computer. This is spooling. So next what we do is there is a subchapter on system calls, which we will tackle next time because we lack the time today. We have 10 minutes left. And in this 10 minutes left, I want to talk about virtualization because we need that for the next time. So maybe some of you heard the term virtual machine already, and we will use a virtual machine throughout the course. The basic concept behind this is called virtualization. And virtualization is the process of creating a software-based simulation of something. You can virtualize a lot of things. You can virtualize networks. You can virtualize CPUs. You can virtualize RAM. You can virtualize a lot of things, right? And you can virtualize, so creating a software-based simulation, emulation of a whole computer. And this is what we call a virtual machine. So we are able to do this simulation for a computer, for a network, even an operating system. Software-based representation of a computer is called a virtual machine. So we can emulate or virtualize. Virtualize is the technical correct term for this. We can virtualize a CPU. We can virtualize RAM. We can virtualize disks. We can virtualize all the components of a computer. So one physical computer, like my laptop here, can run multiple virtualized, like software-based representations of virtual computers. We call this virtual machine. And we use this virtual machine to install an operating system that we use throughout the course. So we are using an Ubuntu operating system, which is Linux-based. And for you to not have to remove your operating system that your computer is currently running, we do this in a virtual machine because you can easily create this. There's software for that. And after the course, you can either keep it or you can remove it as well. So the program managing and executing virtual machines is called a hypervisor. And the computer running the hypervisor is called the host machine, or short host. And the computer that is virtualized is called guest, right? So we have a host computer and multiple guest computers. So you can run macOS on your computer virtualized. You can run Linux. You can run a second version of Windows. You can have multiple guest versions, multiple software-based simulations on your physical host machine using this virtualization technique and using a hypervisor. There are different types of hypervisor. So what you see in these three diagrams here, let's focus on the left one, which is basically the story so far. So we have the hardware, and we learned today that the operating system is an abstraction over the hardware. So kernel here is the core of an operating system. Like this is the operating system software, which we call kernel. So the kernel sits on top of the hardware, and if you remember, like this graphic, the hardware has an ugly interface. You put an operating system kernel on top of the hardware, and the kernel provides processes or programs running on your computer with a beautiful interface. So this is how this works. Then we have two hypervisors. Well, type 1 hypervisor work as follows: that the hypervisor directly sits on the hardware, so interacts with the hardware directly, and provides a software-based simulation for multiple virtual machines. So virtual machine, a computer that is software-based, emulated on a single hardware. So in this case, the hypervisor provides a virtual computer to 3 virtual machines, and each of these 3 virtual machines have their own operating system and are entirely separated. So this is how type 1 hypervisor works. But there is a type 2 hypervisor as well, and this is what how most virtual machines are built up. The difference is, you see it in the diagram, the hypervisor is not sitting directly on the hardware. The hypervisor is also a program that runs on the operating system of the host. So we have a hardware, and then we have an operating system sitting on top of the hardware. And running on that operating system, we have a program that's the hypervisor that can have multiple virtual machines, right? And each virtual machine has an own operating system, and the process in a virtual machine use the operating system in the virtual machine. Well, if you take a plain look at this, you would see, well, does type 2 hypervisor really make sense? Because, well, isn't a type 1 hypervisor more efficient because it's simpler? Well, the answer is surprisingly no. Because when a hypervisor sits on a kernel of an existing operating system, the hypervisor is able to provide the services or directly forward the services that happen in the operating system inside a virtual machine to the operating system out of the virtual machine, like operating system services. The services that the processes require from the operating system here inside a virtual machine are forwarded to the operating system that runs outside. And this is faster than simulating a CPU. In a type 1 hypervisor, the hypervisor has no operating system between itself and the hardware. So what the hypervisor here needs to do is to simulate any instruction here in between the hypervisor and the virtual machine. And as it turns out, it's way faster that the services are directly forwarded to the operating system by the hypervisor. This is faster, like in type 2 than in type 1. So the challenges with type 1 is we have instructions. We will learn what privileged instructions are next time. But it necessitates like emulation of the original instruction set in type 1 hypervisors, which is slow performance. And there are some CPUs, especially the Pentium CPUs, that struggle with this kind of approach that type 1 hypervisors do. Type 2 hypervisors, on the other hand, leverage the host operating system. So there is an operating system there, and the services from one operating system to another operating system are just forwarded. And it turns out that this is way faster. So we are working with a type 2 hypervisor. And now what I want to talk about as the last thing is there's a task, Ubuntu Virtual Machine, that is in our course here, and I want you to do or to complete this task until next time, because the task in Ubuntu Virtual Machine is to create or to install a hypervisor in the first place, right? And the hypervisor that we use for Intel or AMD CPUs is VirtualBox, which is a free and open source version of a type 2 hypervisor. So VirtualBox is a type 2 hypervisor, and you can install it on your operating system. So if you're running Windows, you can install the hypervisor VirtualBox by just installing the program on your operating system. On Macs, on the other hand, it depends on which generation you run. If you have a Mac machine that has an Intel or AMD CPU, you can still use VirtualBox. But as modern Macs use an M2 chips or Apple Silicon, which has a different hardware architecture. And if you remember at the beginning, we had this that, well, a program is a set of instructions, and the instruction needs to be as a set of the machine language. These two architectures, like Intel AMD, have an AMD 64 architecture, and then Apple Silicon follows an ARM architecture. So the instructions are different between these two. You cannot use VirtualBox on an ARM Apple Silicon MacBook. And therefore, you need a different hypervisor. So VirtualBox is not possible. The hypervisor that I propose is called UTM. and all the detailed instructions, how to install the hypervisor and to create the virtual machine and to install the Ubuntu Linux operating system inside that virtual machine. The instruction step by step is in one of these two PDFs. So if you own an Apple Silicon MacBook, then you follow the instructions of Apple Silicon. I'm opening it up right now, and you see, well, I made some nice pictures with arrows or two buttons that you need to press to install this operating system, right?